Welcome, everybody, to the Theoretically Speaking seminar series, and specifically to today's lecture on PACE Tech, Physics and Algorithms Coupled to Enhance Technology. And I've got to say that Theoretically Speaking is actually my favorite seminar series within Simons. I've learned a tremendous amount from each and every lecture that I've gone to on very varied topics, which have a theoretical grain in them and computational as well. And the Simons Institute is a leading venue for theoretical computer science, collaborative research. We convene people from all over the world on different topics that are adjacent or squarely within theoretical computer science. And today's lecture is going to be given by Yonina Eldar, our speaker. Just a few words about Yonina. Yonina is a professor of applied in mathematics and computer science at Weizmann Institute, where she leads the Center for Biomedical Engineering and Signal Processing. She's also a visiting professor at MIT and the Broad Institute, as well as an adjunct professor at Duke. And Yonina is a member of the Israel Academy of Science and Humanities. She's an IEEE fellow. She has received many awards in excellence in research and teaching, including the IEEE Signal Processing Society Technical Achievement Award, the IEEE AESS Fred Nathanson Memorial Radar Award. That's interesting. And Michael Bruno Memorial Award, the Weizmann Prize for Exact Sciences, the Wolf Foundation Krill Prize for Excellence in Scientific Research. And she does incredibly fascinating work in compressed sensing, signal processing, and biomedical applications. I've been to her lab, and it's just kind of, wow, you know, she's working with real ultrasounds, real MRI images. And today she's going to tell us about her work. And thank you, Yonina, for coming all the way from Israel.
Okay, so good evening, everyone, and thank you so much for coming. And thank you very, very much, Shafi, for that very, very kind introduction. It's really a great honor and privilege to be here. And I do want to say it's even more of a privilege that Shafi invited me, because really I want to thank you for being such an inspiration for so many of us, both for your excellence in research and also for being an excellent leader, and also the ability to take groundbreaking science into practice. So that's definitely something that I've been inspired from, and it's really an honor to be able to give this talk. So what I want to talk about today is some work that we, and of course many others, have been working on with the goal of coupling physics and algorithms in order to try and overcome different bounds that we have today on technology. So what I'll try to kind of convince you of today is that by looking together at physics and algorithms, we could develop technology that is faster, smaller, lower power, and could overcome different resolution limits. And what I'll try to do is kind of give the basic ideas behind what we're doing, and then a variety of different applications in different areas like communications, radar, medical imaging, and optical imaging. So today, of course, we live in a digital world where more and more of the processing is being done on digital devices. But if we want to digitally process real physical signals, like this music, for example, coming out of the guitar, then we have to have a way to take this music, convert it into bits, and then once it's on bits, we could process it on our computing devices. So this is really kind of the science behind a lot of the digital devices. And the field that I work in is the field of signal processing, which really gives us the mathematical models and the mathematical algorithms to process these digital bits. So signal processing has had a huge impact on technology, going back to radars in the 50s, and then moving to more modern digital technology, if it's autonomous vehicles, hearing aids, medical images, biometric recognition, and many other applications.
Analog girl in a digital world.
So I really like this song. It's also a good way to wake everyone up, including myself, that kind of captures this essence of sampling, right? So the signals around us, physical signals, are of course analog, they're continuous in time, but of course we get many benefits from operating in the digital domain, and we have to somehow go from analog to digital without losing information. So this is done by a piece of hardware, right, which is called an analog to digital converter, and what this converter essentially does is that it samples the signal at given points in time, and then it converts those amplitudes into bits, okay? So any digital device really has this ADC in front of it that enables the digital processing. So let's see how this is going to work, right? So suppose we have a physical signal like this red signal over here, and we're going to go ahead and sample it in time, right? So we get these blue points, and all we're going to end up with are the blue points, and we have to kind of try and figure out, right, what was the red signal. So, how do you do that? Well, this always reminds me of this, connect the dot that we used to play when we were kids, right? Where we have like all these, of course, here you have the numbers, so you know how to do it, but you have all of these dots, and you have to complete it. Now, why does it work? Why does connect the dots work? For two reasons, right? One, because they give you the points close enough so that you could kind of trace the image. The other is because you have prior information, right? Because look at this, you have an eye, you have an ear, you have a tail, kind of looks like an elephant, right? So even before you connect the dots, you have prior information. And these two things are actually very key in all of the mathematical theories of sampling. So it's the prior information and making the points close enough. Of course, the question is, what is close enough? So going back to the problem we had before, right, we only have the dots. And of course, the true signal we had before, the original true signal, will in fact complete these dots. But there's other signals that will complete the dots as well, right? Like these two signals over here. Now notice that these other signals that I plotted actually vary faster than our original signal. So one way to make sure that we only have one unique recovery is to limit the speed of change. Okay, so this was kind of a very hopefully intuitive explanation of actually one of the most fundamental theorems in sampling theory, which is Nyquist's theorem. And what Nyquist says is that if you want to sample a signal in a way that you could recover the underlying signal, then you have to sample at twice the highest frequency in the signal. Okay, so that is exactly the picture we saw before, that you have to limit the speed of change. Okay, so this is a theorem about sampling. We also have various different theorems about quantization, and these beautiful results are due to Shannon, who's the father of information theory. And for example, one of the problems that Shannon studied is how many bits could we transmit reliably over a communication channel, and that leads to the definition of capacity, which is going to be proportional to the bandwidth and to the SNR. Another set of important results by Shannon is what's known as rate distortion theory, and that basically tells us how many bits we need to represent a given signal up to some distortion. Okay, so if we combine these results by Shannon and Nyquist, we basically have the underlying theory for A to C conversion, and any analog to digital converter today kind of is designed by obeying these theories. Okay, so it looks like problem is solved, right? We have these theorems from many years ago, almost 100 years ago, so what's the problem? Well, the problem is that both of these theorems depend on bandwidth, okay? So if we have higher bandwidth, then both of these theorems imply that we need higher sampling rates and higher bit rates. And in modern applications, that starts being a real limitation, okay? Because today we want to use signals with wider and wider bandwidth because we want to convey more information, or we want to get better resolution, which again requires higher bandwidth. And that becomes very difficult to do from several aspects. One is the actual hardware, so designing hardware to sample at those rates is almost impossible at very high rates. It leads to lots of data that we have to store, we have to process, we have to communicate. This, of course, also leads to latency and many other issues that are, let's say, technology issues. We also have other limitations. So, for example, high sampling rates translate in the context of medical imaging into long scanning times and high radiation. So long scanning times in MRI and high radiation in CT. So at the end of the day, this ADC that we kind of take for granted, right, it's the starting point of any digital implementation, is actually a bottleneck in many different areas. Now, a totally different set of limitations come from physics, right, from resolution limits. So we know that any measuring device that we have is going to be resolution limited, so we can't see with infinite resolution whether it's time, space, or frequency. So, for example, if we look at the famous Abba's diffraction limit in optical imaging, we know that if we're using an optical microscope, then we can't see details that are smaller than half the wavelength used for illumination, so we'll be able to see, let's say, bacteria, but it will be very hard to see proteins and small molecules. Okay, and this is a limitation of physics. It has nothing to do with how good our technology is. We also have the same resolution limit when we look at spatial resolution. So if we're looking, for example, at antenna arrays, like in radar or communication, or even in an ultrasound probe in an imaging device, the spatial resolution is, again, limited by the aperture. And that's why you see, these huge radars in order to get good resolution. So clearly, this is a limitation on technology as well. And these are limitations that are coming from physics, right, not from the device itself. So we see that both the physics and the technology, Shannon and Nyquist's theorem, at the end limit what we could do with technology. And the question is there a good way to overcome that? So basically what we're going to kind of propose is that, if you can't beat them, then join them, right? If physics and technology are giving us different limitations, let's see what happens when we combine them. So basically what we're going to do is we're going to use the math to suggest different ways of transmitting information where the information is not something that we could hear or see directly, okay? So it's going to be kind of distorted information, but it's going to propagate better and give us better resolution. So the math will suggest how we could use the physics to give us information in a different way. And then at the receiver side, we're going to use the math to extract that information. Okay, so this is kind of the principle behind what we're going to suggest in all of the technologies that we're developing, where really the key thing is we don't have to be able to hear or see directly, right? If we get information that's kind of scrambled, maybe it propagates better, maybe it's easier to protect, maybe there's other advantages we could get from it, and then we'll rely on our algorithms to extract the actual information that we need.
So you're saying that because you have limits in the mathematics, that's the way I hear you, in terms of the devices, you're gonna transmit in a different way.
Right. Exactly, but it's not in a conventional way. So it's not in a way that, let's say, if it's an image, if you look at it, it's just going to look like garbage, okay? But I don't care that it looks like garbage because I could use my algorithms later to extract what I actually want to see, okay? So at the end of the day, as long as my device has computing power, I don't need the physics to be direct, right? Like I don't need the waveform to actually convey the information in a way that's convenient for me to hear or see, okay? But that's not the way standard things are done today. Okay, so let me try to make that a little bit more precise by two examples, and then we'll go back and talk about the fundamentals. So let's look, for example, at ultrasound, which is something we've been working on a lot. So ultrasound is wave-based, just like optics, and therefore it's limited in the resolution, okay, because of diffraction. So what you see over here, this is actually a true ultrasound of a patient with a breast lesion, okay, so this is the lesion. And clearly you see there's a lesion here, but you can't see within the lesion, okay, so you don't know what it is. Okay, so the question is, how could we do better, right? How could we be able to see better? So the first thing we're going to try is to use physics. So we're going to use contrast agents, and this is something that we actually did. So contrast agents, what they do is they give you better contrast, meaning they reflect the signal better, and therefore the hope is that, if the signal's reflected better, we'll be able to see better. Okay, so we injected these contrast agents into the patient, and then, you go ahead and take your image, and unfortunately, you do see brighter, okay, so there's better reflection, but that actually doesn't help us because we don't see within the lesion. In fact, in some sense, it's even worse, okay, so we can't see the lesion at all, but it definitely did not give us more resolution within the lesion. But now we can use the math and basically, okay, it's a little bit hard to see because of the bright lights here, but hopefully you could see something. What you could see, could you see anything? Okay, good. So what you can see here is that we can actually see within the lesion, and the way we did that is by taking this image but actually tracking the bubbles as they're propagating through the blood vessels, okay? So this is, and I'll go back later on to how we actually did this, but this is an example of how we're coupling physics and algorithms. So if I tried to track the blood vessels in the original image, I wouldn't get anything because there's nothing to track. On the other hand, the physics alone that injected those bubbles didn't give me anything because it just gave me a bright image. But I know the bubbles are in there. So if I use the physics together with the algorithms, I'm actually following those bubbles, and therefore I could actually trace these blood vessels. And in this case, again, if you're a doctor, which I'm not, but we learned this from the doctors, you could tell, unfortunately, that this is a malignant tumor, okay, because of the inhomogeneity that you could see over here. So by tracking these bubbles, we're able to trace out the blood vessels, which we couldn't do before. So this is one example of combining physics and algorithms, where each one of them alone wouldn't give us a good result. As another example, which is very similar but in a different area, we've been looking at fluorescence microscopy. So we already said optics is resolution limited, and a really, really clever way to kind of get better resolution, and in fact it won the Nobel Prize in 2014, so it's definitely a good method, is fluorescence microscopy, where the idea is that if you want to take a super resolved image, you use these fluorophores and you control the fluorescence in each exposure. So instead of taking one image, you take thousands of exposures, and in each exposure you only have a small number of fluorophores that are actually fluorescing. So then what you could do is you basically pinpoint each individual fluorophore. Okay, so think about like an exposure where you only have 3 green spots, right? So you could just stick a Gaussian, right? Every time you see a spot, and then sum over all of the images, and you'll get one super resolved image. Okay, so this is basically the idea behind fluorescence microscopy that led to the Nobel Prize, and this gives like a 10-fold increase in resolution. So really, really good in terms of spatial resolution, but it does it at the expense of time, right? Because now we need thousands of exposures to get a single image, and therefore you can't use this for live cell imaging. So here again, we use the same idea where instead of doing the fluorophores kind of 1 by 1 or 5 by 5, we actually let them fluoresce together so that we cover the images much faster. And then we use clever algorithms to kind of track these fluorophores and extract the information. Okay, so we'll talk more about that later on. But again, it's similar to the ultrasound example where we take the exposure in a different way, right? We let all the fluorophores kind of project at the same time, but then we use clever algorithms to separate them in retrospect. And that way we can get both very good spatial resolution and very good time resolution. Okay, so hopefully these examples gave some intuition into what I mean by coupling physics and math. And the nice thing is that this leads to new mathematical ideas as well, right? Because once we use the physics to transmit signals in a different way, basically we have new mathematical limits that we could explore on the bounds, like the bounds we said before. Okay, so there's a nice interplay here between the technology and also the mathematical limits. Okay, so what I want to do in the rest of the talk is kind of go a little bit into more detail on how we design these type of technologies and then look at a variety of different applications to ultrasound, radar, and several other communication applications. And at the end, I also want to talk about how we can use these ideas not only to develop technology, which is focused more, let's say, on the signal acquisition, but also for purely digital problems like different deep learning and AI methods that are totally digitally driven, right? There we're not talking about acquisition devices, but these same ideas of using algorithms and coupling kind of structure into the algorithms are useful even for totally data-driven problems. So any questions so far? Okay, so let's move ahead and talk a little bit about how we actually do this. And all of the pictures you see here are pictures that, of systems we've actually developed in the lab. So if we look at how systems are developed today, they're actually developed in a very modular fashion. So typically we'll have some transmitter, let's say an ultrasound probe or a radar signal, and we transmit the information. On the receive side, the first thing we typically do is we have a sampler, right? Because we want to move to the digital domain. And this sampler is typically going to sample by the, not typically, always, by the Nyquist theorem or more. And then we have the quantizer, right? We have to convert to bits after we sampled in time. And this is typically done by Shannon's principle, by rate distortion theory, which essentially tells you that for every additional bit, you get 6 dB in SNR. So depending on the SNR you want, you choose the number of bits. And then after we sampled and we quantized, right, so we get all of this information, and then we start doing the processing, right? So let's say in radar and ultrasound, you're typically going to beamform the data, so you get all of this data and you focus it to a certain direction, and then you get your image or your delayed Doppler map. So this is kind of the standard way systems are designed, and the disadvantage in this design is that each block is optimized separately. Okay, so it doesn't take into account at all any of the other blocks in the system, and as we're going to show, this is actually very wasteful. So what we want to do instead is do the design together, okay, not break it up into blocks, where in this joint design, there's 3 things we take into account. So one is any structure in the input or in the system. And since we're also very often changing the transmit, right, we're changing what we're transmitting, we can induce structure, and we'll see that that's very useful. Okay, so one thing to take into account is structure. The other thing is the output task, right? Since systems are designed separately today anyway for each application, right? Each application has its own individual chip or hardware. Why not take that into account rather than doing things generically? And for different tasks, we may be able to sample and quantize in different ways that are more resourceful than what is done today. So that's the other thing we take into account. And finally, like I said before, we take into account that the output of the system does not have to be meaningful. It just has to convey the information, and we can use mathematical recovery to extract the information. Okay, so that sounds rather trivial, but again, it's just not the way that systems are designed today. So like
these 3 things, you take it for each box. So like a sample, you assume some structure in your input.
Exactly, in my input or in my output, in the output task. Okay, so it could be that there's no structure in the input, but there's structure in the output.
So if you had different tasks,
I would have a different sampler.
you'd have different samples.
Exactly, exactly.
Compress the data so it could be used for many tasks.
Exactly, exactly. And of course, at the end, you want to have things that are generic in the sense that I don't really want to change it for every application, but if I could do a class of applications, then I could benefit a lot. Like for example, then people will often say, yeah, but that's not good, you want things that are generic. But if I build a radar system, right, then I'm building a radar system. The chips in a radar system are designed for a radar system. They're not designed for an MRI system. So anyways, at the end, you're building things that are specific for that system, then why not take into account that it's a radar signal rather than an MRI signal? So it's done anyway, but not on this level of the sampling and quantization. Yeah, but that's exactly the idea.
But you lose a lot of good mathematical properties like convexity or Nyquist theory, rate distortion theory, not to mention the non-determinism that comes with deep learning. You run into two initial seeds if you do end-to-end, right?
Okay, so you could say that I lose.
There is no free lunch, actually. That's a theorem of learning.
Okay, so I view it in a slightly different way, but thanks for that comment. So you're saying I lose Nyquist theorem. I say I benefit because I have a new theorem. So I get to develop new theorems that take into account the structure and the end-to-end task, and then I have new bounds, and those are the new bounds that I want to achieve. So you're right that I can no longer apply Shannon and Nyquist theorem, but the goal is to develop equivalent theorems that take these things into account. So for example, we developed rate distortion theorems that are end-to-end, that are not just for quantization, but that are end-to-end rate distortion theorems. Or we've developed sampling theorems that take into account the structure in the system. So those kind of replace the Nyquist theorem. But they're the same thing, right? They say, given an analog signal and given the structure, this is the minimal rate, and here's how you recover. Okay, so you could view it as losing, or you could view it as benefiting from new theorems. I hope that addresses what you meant.
To a large extent.
Okay, good. So hopefully as I go through, it will be substantiated. So the other thing the comment I made before, and I'm just going to make it again, is that here we're focusing on kind of analog to digital systems, but we could use the same ideas in purely digital systems and design kind of computational methods that are taking structure and task into account, even when they're data-driven. And we'll talk a little bit about this at the end. It's not the main focus of this talk today, but we have two recent books where we kind of go into this in more detail, one in the context of communication systems and one more in the context of medical imaging, particularly in COVID-19, but it talks about medical imaging more generally. Okay, so now let's start looking at some classes of examples to make this all hopefully a little bit more concrete. So what do I mean, for example, by structure in the input or in the signal? So one of the early examples we looked at more than a decade ago was this multiband problem, where we have a signal that's constructed from several bands of information. Each band is narrow, but they could be spread over a very wide regime. Okay, so the Fmax could be very high. So this is a classical example you get in different communication problems, in different defense problems, in cognitive radio, etc. So the standard approach to these types of signals is that because you don't know the carriers, you have to sample at Fmax, right, following from Nyquist. But that is, if you just think about this from like an information theory point of view, that's very wasteful, right? Because Fmax could accommodate any signal that is full from 0 to Fmax, but these signals are never full. They never occupy the entire frequency content. Okay, so intuitively, there's waste here, but of course the question is, how do you do that in practice if you don't know the carrier frequencies? Now here, of course, I'm looking at communication, but we get the same problem in any medical imaging application where you image with multiple frequencies. So we've used this for imaging problems as well. So this is one class of structure that you could think of. Another class of structure in the time domain, which is actually prevalent in many applications, is the stream of pulses model. So in this case, what you actually receive are a series of pulses where you don't know the time of arrival and you don't know the amplitude. So this happens, for example, in radar, where you send a pulse, and every time it hits a target, right, it's going to be reflected back. So if you could figure out these times, then you get the distance to the target, and if you could figure out these amplitudes, then you could extract the velocity of the target. Okay, so this is how radar works. But what a radar system does is that it just samples at the bandwidth, right, which could be very high. It doesn't take into account that I actually am always going to have a stream of pulses. That's just how radar works. And in fact, you get the same example in ultrasound. So although ultrasound, at the end it looks like an image, but the way it's formed is exactly like radar. Within the probe, you send pulses, you get pulses back, and basically to plot a line in the imaging, you're plotting these times of arrival and the amplitude. So it's very similar to radar. Okay, so this is an example where this is just the way the system is designed, right? So it's always going to have pulses, but it's not exploited today in the system design. So in fact, ultrasound is a little bit more complicated than standard radar, and that's because within the probe, you typically have between 128 and 256 elements, so there's a lot of data. Okay, the data is taken in all of these elements, and then you beamform it, okay, so you align it in time to focus to every point in the image. But the issue here is that it's near field beamforming, so you get this kind of complicated nonlinear equation, and then the question is, let's say somehow I could sample at a low rate, but then how do I beamform at a low rate, right? Because beamforming is basically aligning signals and summing them up, and if I sampled at a low rate, then it's not clear how I could align on a very small grid. So the difficulty in these problems is not only the sampling, but also the processing. And of course, our goal is to do everything at the low rate, not to have to go back to the Nyquist rate just to do the processing. So we'll see later on that this could be done, and this is what we call compressed beamforming. So not only could we compress the sampling, but we could compress the whole processing chain as well. Okay, so those are kind of two examples. Hopefully they give some concrete applications. There's of course many more examples you could think of. But what's nice is that all of the examples, the ones that I showed and others that I didn't show, they fall very nicely into a joint uniform mathematical structure. So we can show that all of the examples obey this mathematical model that's called a union of subspaces. And it's a very simple model. So what this model says is that we know a priori that our signal lies in a subspace, in a low-dimensional subspace, but we don't know which low-dimensional subspace. Okay, so all of these examples, like the ultrasound and the multiband and whatever, once I know, for example, the times of arrival, or once I know the frequencies, I lie in a low-dimensional subspace. The problem is I don't know the times of arrival, right? So I have an uncountable number of options. Only one of them is correct, but I have many, many options. Okay, so this is just mathematically a union of subspaces model, and the nice result that kind of, this is an example of something that replaces Nyquist, for example. So a nice result we can show is that when you, to sample over a union, the rate that you need is the rate associated with the sum of two subspaces in the union, irrespective of how many I have, even if I have an uncountable number. So the Nyquist rate is actually the rate associated with the sum of all subspaces, whereas what we can prove is that the real rate you need is the rate associated only with the sum of two. Okay, and clearly 2 is much smaller than all, and this is really where the kind of low rate comes in. Okay, but of course this is just the lower bound. It doesn't yet tell you you can achieve it, but it does give hope that you could sample at rates that are much lower than the Nyquist rate. Okay, so that's an example of a theorem that replaces Nyquist.
Does it hold for low-dimensional manifolds or just in subspace?
It does, yeah, it would be the same. I'm just showing subspace because it's easier, but the same thing holds. Okay, so that was just the lower bound. Of course, the question is, how do we actually achieve it? So the nice thing is that we can actually develop hardware that we could prove that achieves.
When you say low bound, you mean that's a possibility here?
Right. It's not an achievability yet. It just says that, you know, this is the sampling rate is lower bounded by this, but maybe the actual rate is over here, and that's just a lower bound. So to show that it really replaces Nyquist, I have to convince you that there's a way of doing it. So this is something we worked on already many years ago called sampling, which with the idea of being compression and sampling done together. And what we can show here, I'm showing it pictorially, but of course you could prove all this. So what we can show is that this method I'm going to now describe actually always achieves the lower bound. So what is this method? The idea, let me give the intuition before I go through the details. So the intuition is, right, we have all of these options of subspaces, and we don't know what the correct one is. So what we're going to do is we're going to alias them, okay? We're going to take all of these options and project them onto one lower dimensional space. That lower dimensional projection has a part from all of them, okay? It's like we're linearly combining them and collapsing them onto a low dimensional space, okay? The good news is that once it's in a low dimensional space, I could, of course, sample it at a low rate because it's now low dimension. The bad news, or what looks like bad news, is that now it's all linearly combined, so I don't know which was the correct one. Okay, so that's kind of the linear combinations or the aliasing that we're doing in the transmission, so to speak. But then what we can prove is that after we do these combinations, if we do them correctly, we could, in fact, from the low dimensional projection, extract what was the correct one and then go back and recover the signal. Okay, so that's kind of the intuition. And the way we actually do it in hardware is as follows. So we take our signal, we multiply it by a periodic function. Here we're doing it with a few, but we can also do it in a single channel. This is just for robustness. But if there's no noise, we could do it in a single channel. So we multiply with the periodic function. And from basic signal processing, if I multiply in time, right, I'm taking convolution and frequency, and a periodic function in time will always look like a stream of deltas in frequency. Okay, so this is cool because we get aliasing for free. So multiplying in time is convolution and frequency. Convolution with a delta stream is aliasing, right? What will happen is if, let's say, this is our input, then the convolution with this will take the signal, move it all the way to the right, move it all the way to the left, and sum it up. Okay, so we're getting aliasing for free. We get something that looks like this. But then the point is that we don't need all of this. We could take just one band. Okay, so this is a low-pass filter. We take one band, and then we could sample it at a low rate. Okay, so we're sampling at a low rate. That's cool. We have low-rate samples, low-rate quantization. Everything's nice and simple. But what we're sampling is this alias version. Okay, so now we have to go back and figure out what was our correct signal. Okay, so this is how it's done in hardware. We have the pre-processing, which is this. We have the acquisition at a low rate. And then to go back and figure out which was our correct index, we use compressed sensing theory, okay, which is a digital theory, but it after we've sampled, we are in the digital domain, and then we could use compressed sensing. So I'll say more about how we use compressed sensing in a second, but just to show that this sampling method that I just hopefully gave an intuitive description of, we can actually prove mathematically that A, it achieves the minimal rate in all union of subspaces models, and furthermore, it has various different optimality properties, even in the presence of noise. So we can show that it achieves the Cromé-Rao bound, which means that it gives us the minimal mean squared error from all sampling rates when there's noise. And it also minimizes the worst case capacity loss. So if we're thinking of this in communication context, this would be optimal in terms of capacity as well. Okay, so like I said, what we do is we do these combinations, and after we have our combinations, we still have to figure out what is the correct signal. So the way we do that is that we take these linear combinations, and then we use compressed sensing to get basically an indicator to which are the correct subspaces. Okay, so those of you that may not be familiar with compressed sensing, basically compressed sensing is a digital theory that allows us to recover sparse vectors, meaning vectors that could be very long, but have only a small number of non-zero values from these linear mixtures. Okay, so in our case, we have analog signals, right? I can't just, multiply them by a matrix. But after we've sampled the way we have, we could set up the problem this way, where X is basically an indicator function to the correct subspaces. And once I know the correct subspace, I could recover within the subspace. Okay, so hopefully that kind of makes sense, at least intuitively. And of course, in our books, we go through much more detail. But then just one thing to point out is that compressed sensing was originally developed as a linear theory. Over the years, we, and of course many others, have worked on extending it in many different ways, for example, to nonlinear measurements, which is very important in optics. So we've worked a lot, for example, on phase retrieval for problems where there's statistical sparsity and many other cases. Okay, so even though the vanilla compressed sensing is kind of limited in terms of applications, but there have been many, many extensions that we and many others have worked on in order to enable application of these ideas to a broader set of areas. Okay, so that kind of sums up, sorry, yeah.
Just what's the connection of compressive sensing and deep learning?
Oh, so there's been, sorry, yeah, I kind of skipped that. So there's been the standard way to recover signals from compressed measurements is using, let's say, L1 recovery or OMP, those kind of standard algorithms to do that. In recent years, there's been a lot of work on using deep learning to recover from the compressed samples, and that allows you to kind of move beyond strict sparsity. So you could look at more elaborate structures rather than just pure sparsity.
So the deep learning comes after you compress.
Right, yes. We don't use, again, in what we're doing, hardware at the end, and this is something that, sometimes people ignore, like you could write anything on paper, right? But at the end, when you're talking about hardware, the input is a true waveform, okay? So I can't multiply it by a matrix or do other things to it. It's not, it's continuous, right? So we don't use any of this stuff to sample the signal. The way we sample is always these mixtures that give me aliasing. But after I sampled and I have digital samples, then I can use these ideas to go ahead and recover. So deep learning basically just extends, the possibility from strict sparsity to more elaborate types of structures. And you could like it or not, right? I mean, you don't have to use deep learning. You could still use more systematic methods.
I don't remember that it's working in the context of compressive sensing.
Sorry?
I don't have recollection that it actually works in context.
So again, it really depends on your data, right? Like if your data does not have structure, then it's not going to work. If your data does have structure, then you could use deep learning methods to find that structure. Personally, I'm not a big believer in using generic deep learning for many things. I think in most cases you could use model-based AI, which I'll talk at the end, but there has been work on it, so I'm mentioning it here. So there are a bunch of papers, by people who originally worked on compressed sensing on how you could use deep learning for more elaborate forms of structure. But the point is that I could connect that. Once I have my compressed samples, I could use any of these techniques to recover.
So one more question. If you go back to 2 slides back when you have that long n by n matrix, you have to have some idea of what n is in order to make n the right number, or how does?
Yeah, okay, really good point. Yeah, that's a very good point. So that really comes from a union model. Okay, here I skipped through the math, so I kind of all of that brushed under the rug. But it's like saying in Nyquist theorem, right? So in Nyquist theorem, I have to know the bandwidth to know at what rate to sample. So it's the same thing in the union model, right? I mean, that's part of my model. My model tells me what are the dimensions of the individual subspaces. Okay, so that's something that I'm assuming is part of my model. Of course, you could always look at practical problems when I don't know that exactly, which is the same as saying in the Nyquist case, what do I do if I don't exactly know the bandwidth? Okay, but assuming if you're just looking at the mathematical theorem for a minute, then that's part of the model.
And roughly speaking, how much bigger should n be compared to m?
Yeah, okay, that's a really good point. Right, right. So that kind of that does come from compressed sensing theory, and it's nice that it applies also to the analog domain. So that's this k log n, okay? So yeah, okay. But roughly, I mean, if there's no noise, then 2k is enough, okay? If x is k sparse, then 2k measurements is enough. Okay, if you don't care about noise and you don't care about computational complexity. The log n comes from the fact that A, you care about noise, and B, you want to do this in a computationally efficient way. So you pay a price, a log n price. But it's usually quite a big savings with respect to n. Okay, does that address? Okay, good.
So the K here is what you know is going to be sufficient for solving a problem?
Yeah, so for example, let's go back, let's say, to the multiband problem. So the K would be the number of users on the channel. Okay? So the Nyquist rate, right, is the bandwidth, which could be very, very large. But let's say I only have 3 users on the channel. So K would be 3. Okay, which could be much, much smaller than the bandwidth. Okay, so there is the issue here, right, which I'm kind of ignoring for now, as, you know, how do I know the number of users or an upper bound on the number of users? But again, that goes back to, like, in Nyquist, how do I know the bandwidth? So from a mathematical perspective, you're assuming this is part of your model. In practice, the nice thing is, again, like in many other cases, I don't really have to know it, right? I just have to sample at a rate that would accommodate enough users. And then, you know, I could do this like what we do in practice very often is we do this in an adaptive fashion, okay? So I start with like a little bit maybe higher rate, and then I could recover, and if I see that I only have a small number of users, I could reduce the rate. Or you could do the reverse. You could start from a low rate, and then if you get garbage, you have to increase the rate. But it could be done adaptively.
Can you detect that you got garbage?
Yes, you can actually.
You got the right answer.
Right, no, but you could detect that you get garbage because, and that's a nice thing here, is that if you didn't sample at a high enough rate, you actually will not recover a sparse vector. You won't get a wrong sparse vector, you just won't recover a sparse vector. Okay, which is actually really cool, and that's what we use. So what we do in practice is usually we start low and then increase, and the thing is that you actually do get garbage if you're at the wrong rate. Okay, so it's not like you get a wrong feasible answer, you just get garbage. And you could prove that actually. Yeah, so that's kind of one of the nice mathematical features here. Again, but all of this is, you know, if you do the mixing correctly. So you have to mix enough to make that happen. Okay, good. Where was I? Okay, good. So that's kind of what we wanted to say about structure. Other important things when we're talking about sampling are, for example, dynamic range. So dynamic range in general is the difference between the maximum and minimum value that you could display, right? So here you see, for example, in ultrasound, well, on the projection, they all look bad, but if you look at this on the computer screen, so this is an ultrasound with kind of broad dynamic range, so it looks okay. I mean, you see the gray levels, and this is a machine that doesn't have good dynamic range, so basically you just get a clipped version. Okay, you could see it in images, and we've all experienced this, right, on our phones. Of course, today there's different corrections for it, but if you try to take a very high dynamic range image, then you're just going to get clipping. Okay, now this becomes a real concern in systems, in like modern systems where you have to accommodate very different classes of signal. So if I have the same receiver for a communication user and for a radar user, then, you know, one of them is going to saturate the receiver. So this is actually a real concern. So here again, we use this notion of aliasing and mathematical recovery. So what we can show is that instead of getting clipping, what we could do, let me just skip ahead. So in a standard ADC, you would get clipping, okay? If I have a signal like this, and every time it's higher than the dynamic range, it just gets clipped. What we do is that we use a modulo operate, just a mathematical modulo, okay, before we sample. And this is like aliasing, right? Because if you look at the signal, it looks all aliased, right? It just kind of looks like garbage. But the nice thing is that we can show, okay, so this is what it's going to look like in an image. We're basically folding everything to a given dynamic range. So, of course, this looks bad, right? But the nice thing is that we could prove that this contains all of the information, and we could extract the original signal after a modulo operation, okay? So this is actually real data, okay? So we get this folded image, and we could go back and recover the underlying signal, and we could do this, of course, for continuous time signals as well. So this is kind of to address the dynamic range issue. And again, it's just based on, you know, mathematical theory that shows that if you have a band-limited signal, you could recover it from the modulo samples. That's actually quite counterintuitive, but anyways, I mean, you could prove that, so that's kind of cool. And you can also prove that you could do it in a robust way.
Is the last one supposed to be better than the first one? No. It's supposed to be the first one rather than clipping. So in a standard ADC, you would just get clipping,
okay? It just clips it. What we do is we give you garbage, okay? I just fold it, but then, I mean, you're not gonna actually see this because I'm gonna give you this, but the point is that I fold it and this is what I sample, okay? But mathematically, I could prove that all of the information is here in these samples. So then when I put it through my modulo recovery, I end up getting this. Okay, so this is supposed to be better than this.
And to begin with, what was,
This was the input. Okay, so this has very high dynamic range, and then a standard ADC would just clip it. Okay, and what we're doing is we're first folding it. Okay, so this looks bad, but the point is that this fits within the dynamic range, and this has all the information in it about the original signal.
So I have a question about the modulo operation. Right? Is the modulo operation here cheaper than adding more bits to my?
Yes. Yeah, so dynamic range, and you know much better than I do, but dynamic range is a huge issue. It actually consumes most of the power of the ADC, right? Because what you usually do is that you have like an automatic gain control in order to fit the dynamic range, and that is super power hungry.
just to get a linear A to B, you have to trim the resistors after they've been produced to match the bin intervals. It's a very expensive.
That's actually one of the most expensive parts of the ADC. So it's kind of cool, right? Because the modulo is very cheap. It's easy to do modulo. It's just not intuitive, right? Because it looks like you've lost information, but you could, again, and I'm not saying that you don't lose information, it's just that if the input is band limited, you have, that's a strong enough prior to recover that lost information.
Actually, I think of the modulo as just keeping the LSBs or the hypothetical larger.
Right, but not exactly, no. Because it's, the modulo is operating in a different way, right? It's not the same as LSB. Just look at this example, right? So it's not exactly the same. Because it's folding it first, right? I mean, you have the jumps of 2 lambda.
It's discontinuity in the module.
You have the discontinuity, which is, it's counterintuitive because the discontinuity actually increases the bandwidth. Okay, so you would think that if I have discontinuities, then now it's going to be harder to sample. But the thing is that those discontinuities actually give me the exact information that I need in order to recover the signal. So they're going to be aliased, okay, which is why you get junk. But again, it's like in compressed sensing. I have aliasing, but it's useful aliasing. So it's the same thing here.
This just reminds me of in the old times, there was this theory of projections of the convex sets where you want to find the intersection of the complete sets and projecting back and forth. So in this case, one set is sort of band limited signal, and the other one is the modulo.
Is the modulo, yeah.
Finding the point of the intersection of the two.
It is very similar. These ideas are similar. The point, I think, is that, you could do projection onto convex sets for a lot of things, right? The question is, are you guaranteed in advance that you have a unique recovery?
Oh, right.
Right? So you could project, but are you going to get the right result? So
This example, did you do iterative algorithms?
yeah. Oh no, it's not closed form. It is an iterative algorithm, but you could prove 2 things. A is that you could prove that there's a unique solution. Okay, so that's kind of a theory result. B, you could prove that the iterative algorithm will converge to the unique solution. Okay, so those are kind of, again, I'm not going through the math here, but yeah, those are the 2 mathematical aspects. There's A, proving uniqueness to begin with, and then B, proving that your iterative algorithm converges to that unique solution. And we do use a form of projection onto convex sets. We just use a more elaborate, it's like projected gradient, okay? So it's kind of like projection onto convex sets, but we're using, we're actually doing a trick, right? I'm also using the fact that I know the jumps have to be multiples of 2 lambda. Okay, and that's actually crucial, right?
One more constraint.
Exactly. So every discontinuity has to be a multiple of lambda, which is a discrete constraint, but it's actually we could prove it's actually a very useful constraint.
Unwrapping phase.
It's like phase unwrapping, but the difference is that I could prove uniqueness to begin with. Okay, so phase unwrapping is like a very difficult unsolved problem, right? Because in general, you can't unwrap the phase. Here I can. I could prove in advance that I can. Again, I mean, that's the counterintuitive part, right? Okay, and then another thing that, of course, again, many people have been working on, but we've been doing this in a slightly different way, is looking at what's called time encoding machines, so changing the way we sample. So rather than standard samplers have a clock, and then every given point in time, whether it's Nyquist or sub-Nyquist or whatever, there's a clock, and it tells you, okay, every point in time, take an amplitude. What we're doing here is a little bit different, so we're saying we're going to sample every time something happens, okay? And Abigail, this is like a little bit of like level crossing, just we're adding an integrator first, okay? So we're saying we're gonna integrate the signal, and every time the integral of the signal passes a threshold, I'm gonna tell you the time at which that happened, Okay, so it's a different representation of a signal. But the nice thing again is that first of all, we could prove that this is a unique representation of the signal. We could also prove that you could do this at the same sub-Nyquist rates that we showed before. And the nice thing from a practical point of view is that this does not require a clock. So it's much cheaper from a power consumption point of view. And we could actually show that we need fewer bits. So in terms of quantization error, this is more robust to quantization error. And intuitively, that's because an amplitude, let's say, of a band-limited signal could change quite a bit. So you could need a lot of bits. But on the other hand, if you look at the timings, their differences are much smaller. Okay, the time between events are actually smaller, so you need fewer bits to represent them.
And of course, if your signal was high pass and didn't have a low frequency component at all, you might be able to get away with the integrator, right? You can just look at the level cross or the zero cross.
Right, but I actually want the integrator because if I'm looking at, so let me actually show an example. So we've been looking at this, let's say, for continuous monitoring of, let's say, ECG, okay? Something where you really want low power and low number of bits because you're doing continuous monitoring. So, for example, here, okay, this is showing what's happening. So this is the signal, this is the integral, and then these are the events. So if I was just going to look at the events themselves, right, then if I don't sample enough, then I might miss the event, okay? But in a sense, because I'm integrating, I'm smearing the event out, and therefore I could get away with a lower sampling rate. So the integral is helping me reduce rate, actually. But the nice thing is that it's invertible, okay, that I could prove that I could still recover. So if I didn't have the integral, I'd have to sample more densely.
No, but if your signal was super high frequency.
I would still have to sample more densely because I have, like, this is high frequency when I have a pulse, right? But then I need the samples to exactly capture where it happened. And I don't want that. I want to be able to sample at a low rate. So if I integrate, I'm smearing out the event, and then I could use fewer samples. But the cool thing is that I could still go back. Okay, so that's why it's different than just regular level crossing. It also turns out that it's more robust because the integral, of course, integrates the noise. So it also gives you robustness. So it gives you a variety of other properties as well. But it does also reduce the rate and reduce the quantization rate. Okay, good. So I don't know, how much time do I have? Because I'm going like slow because I'm happy for all the questions. But I'm trying to think like what's my overall time frame?
I think we're supposed to end in an hour, right? You get questions? But
Yeah,
you have to
so
take
you've
a
got
question.
another.
So maybe take it 10 minutes after the hour because we'll be taking questions as we go along.
Okay. Oh my gosh, I'm like not even a third way through. Okay, so all right, I'll speed up here a little bit. Okay, so let me blah blah blah. What? Oh, this was fast? This is slow. Okay. No. I'm super happy for all the questions because they make it much more interesting. I just want to know my time frame so I don't keep people here when they're dying to leave already. Okay, so let me just.
The whole time frame with questions is still 7:30.
Yeah, so you
Okay, half an hour.
Okay, good. I think questions as we're going along is better, right? Because then it kind of makes it more, okay, good. So one of the things that we've been doing at Weizmann in the center that we started is really trying to take these ideas into practice. So we started the Biomedical Engineering Center in order to really kind of try to translate these ideas both into technology and medical applications. So I'm just going to go through this quickly and then go back to some examples. So within the center, we basically have four kind of pillars: the theoretical research, and this goes back to your question about bounds, et cetera. So at least to me, one of the fascinating parts is actually developing all of these theorems, right? So that's part of what I enjoy. So of course we do a lot of theoretical research. Then we have the lab itself where we develop the boards and all the technology. We have a clinical arm where we work very closely with a lot of different medical institutes to translate these things into clinical advantages. And we have a forum that we started on campus that we call the BEST Forum. So between science and technology, to try to see how we could use technology for more kind of scientific discovery problems. So in the lab part, we work closely with different companies to try and see, where we could get different advantages by using these technologies, mainly in radar, medical and optical imaging, communications, and more recently at Weizmann and more biological problems. This is just a subset of some of the things we work on, but I'll skip through that. And then in the clinical arm, we work closely with hospitals to understand two things. One is where could our technologies potentially have an advantage, but the other, which is more interesting, is kind of really understanding some of their unmet needs and seeing, okay, could we address them with some of these tools? So this is a subset of some of the things that we're doing more in the clinical domain, and we work with a variety of different hospitals. Sorry, I was like speeding up.
It's sort of more general audience. So like COVID, what did you guys do?
Yeah, so I'll get to that later on, but like in COVID, we use these principles of models, what we call model-based AI, which I'll get to at the end, in order to get very efficient COVID detection. It's actually been implemented in Beilinson Hospital during COVID. So what we do there is that we use these model-based AI from a simple X-ray to detect if it's COVID or non-COVID. And that's actually a very hard thing to do. I mean, standard AI, you would need, I don't know, thousands of examples, which we didn't have. So we had a database of like 200 examples that were all, not a good database, right? They're all taken from different machines, different hospitals. One, the patient is lying down. The other, the patient is sitting. I mean, not your standard AI set that you would like, right? So a standard AI algorithm would not work well on them. But by using this model-based AI that I'll explain later on, we were actually able to get over 90% detection rate. So that's kind of an example of how we use it in COVID.
With just 200.
Yeah. The whole point is not to use large training sets. So I'll get to that. I mean, most of these examples I'm actually going to talk about if we get there. So yeah. No. I'll get to these examples. Okay, so let me move a little bit to applications, and then I'll skip some of them, and so that we have time for also the model-based AI. But one of the examples that we're kind of really excited about are things that have to do with ultrasound. And the reason is that ultrasound is a very convenient medical imaging device, right? I mean, there's no radiation. You don't need like a big machine like you need in an MRI. So it should be more accessible. But today, there's various different limitations with ultrasound. We'll speak a little bit about them. So one of the first things that we showed is that we could form an ultrasound image with much less data using the ideas that I showed until now. And why does that help us? So now, instead of having a machine, we can actually just develop a probe where we do the sampling directly in the probe. And today, that's not done in the machine. So the probe here is totally analog. That's why it goes through a cable, because it's actually an analog cable. And everything is just sampled within the machine because of the high rates. But now we could do the sampling directly into the probe, and then what comes out of the probe are bits, okay, like it should in the digital world, and those bits could be conveyed over any Wi-Fi channel, for example, to an iPhone that a doctor holds and can see the image, or over the cloud to some remote processing. So
hello everybody.
This is a demo of Dr.
I would like to show you here a demonstration of a normal heart. What we can see here is an echocardiography of the subject's heart. We can see a
So what you see here, the data is going directly from the probe to a local machine, to a remote machine, through the cloud, and then to an iPad.
Atrium and the right atrium. We can see the different structures of the heart. We can see the mitral valve and the tricuspid valve. We can see the nice motion of the leaflets. We can see that actually there is good ventricular function and there is no pericardial effusion. The picture itself is very good, very crisp, and we can demonstrate very nicely this subject's heart.
Okay, now he's scanning directly to the tablet. So the point is that it works just like a high-resolution machine would work. But the other nice thing is that now we're basically freeing the data. So a standard ultrasound machine, besides the fact that it's huge and costs $300,000, it gives you an image. It doesn't give you data. Okay, but now we're actually freeing the data. So once I have the data, I can use more sophisticated algorithms on the data. And for example, this is true data, so again, it's a little bit hard to see on the screen, but we're getting better contrast and better resolution just by using better algorithms on the data itself. And the other really cool thing, at least for me, is again going back to the physics. So now that I have data, instead of just looking at an image, I could look at physical properties of what I'm imaging. So if you think about it, right, if I'm reflecting tissue, different tissues will have different physical properties. So for example, now that I have data, I could solve physical equations and map out the speed of sound of an image. So together with the regular image that the doctor's used to seeing, I can now give the doctor an image of speed of sound. And here, for example, this is real data. So you can see here, there's a growth here, okay, there's a lesion here, but it's actually hard to see where it is, right, if it's here or somewhere else. But now when I look at the map of speed of sound, it's clear that it's here, and this tissue is behaving differently because there's a tumor there. Okay, so I'm not saying to use this instead of an image, but you could use it together with an image now that you have the data. And all we're doing really is solving the wave equations on that data. But today it's not done because you don't have access to the data, you just have the image.
So what's the data here?
The data is the actual, so what I'm doing is the data in ultrasound is I send a pulse, I get reflections coming back. And what a standard machine does today is it takes all those reflections, it beamforms it, okay, so it basically collapses it all to a line. Okay, and then it moves on, takes another data set, collapses it to another line. And that's the image that you get. Okay?
And then a doctor looks at it and interprets it.
Exactly. But these images are not easy to interpret. Ultrasound images are not easy to interpret, right? They're just these gray level images.
So you were saying that the data is...
So I'm saying, okay, the data itself, besides just thinking of it as like beamforming, right, as plotting lines, these are physical wave equations, okay? And we know how to characterize them. They're just complicated, right? But they're physical wave equations that I could solve. Now I'll say a minute about how we solve them, but it's wave propagation, and I could write down an equation that says if I'm looking in a certain area, right? And let's say I'm looking at the speed of sound. Let's just talk about speed of sound, for example. So the speed of sound at every pixel depends on the properties of the tissue in that pixel. And I know how to write that down, right? There's a wave equation that describes that. So the wave coming back at me will behave differently if it hit, the speed of sound, of the wave coming back at me is going to be different if it came from a tissue with a tumor than if it came with a tissue without a tumor. Okay, so I can actually write down the wave equations where the speed of sound is a parameter and extract that parameter from the data. Okay, and not just think of it as like beamforming to create an image.
So using ultrasound in different medical, if it's the heart or the womb or whatever, it will be different probes or you have different data.
So the probe would be the same, but the data is going to be different. Exactly. But these things are not exploited today because you just form an image, right? But now that I have the data, I could say, okay, why not solve the wave equations? Now, why do people not solve wave equations? Well, because it's complicated, okay? But when you don't have access, like if you're doing this all in a machine, and you have huge amounts of data, then this is very difficult to do. But once I'm doing it out of the machine, right, because now the data are just bits that I'm moving to some server, and I don't have huge amounts of data anymore because I subsampled all of it, then it becomes realistic to solve the wave equations, especially because we're using modern tools, right? So I'm not, I don't know how people used to try and solve wave equations, but basically by doing discretization and different Fourier, it's very complicated. Today, I could just do back propagation. So I'm not doing deep learning, but I'm using the machinery that was developed for deep learning, which is basically optimization solvers, and I'm using them to solve the wave equation. So I'm not using deep learning in the sense that I'm not learning anything from training data, but I'm using deep learning tools to solve the wave equation.
Theoretically,
One sec, sorry. Just
This is extremely exciting, and using wave equations to characterize tissue, which, for instance, ultrasound does very poorly. How do you expanded this into CT, into MR? I mean, all of these technologies really don't characterize tissue directly, and they give you images which people can then relate to syndromes as they see fit.
Right.
This is a completely different approach.
Yeah.
I'm just wondering it's pretty obvious the path to be taken. I just wondered if you've taken it.
Yeah, no. So thank you so much for the enthusiasm. So as you can tell, this is a paper from like just now. So we just started working on this, and we would love to collaborate with people who know more about, the physics of the different modalities. But I totally agree. I mean, that, to us at least, that's the path, right? The path is in getting the data itself and then using modern machinery, not necessarily for learning, but for solving equations efficiently. Totally. I mean, that's, again, this coupling of physics and algorithms. So I'm happy you find it exciting, and we definitely would love to collaborate, in different domains. The nice thing about ultrasound is that I could do it in the lab, in my lab, right? Because I don't like MRI and CT, is much more complicated. This, I could do in my lab. I could take apart their machine, so it's easy for me to play around with by myself. MRI and CT, of course, you have to work with people who have the machinery, but we'd love to do that, so definitely. Sorry?
Steal their data.
I'd like to collaborate instead of stealing, but you had a question also before. Okay. So I'll skip this maybe. We could do ultrasound and radar are very similar. So everything we do in ultrasound we could do with radar. But in the interest of time, I guess you trust me, we could do this in radar. All of these movies are on my webpage, so you could take a look at them. But in the interest of time, maybe I'll skip through the radar. We've been looking a lot at different radar applications like autonomous vehicles, where again, gaining resolution and reducing cost is very important. We could scan, let's say, 360 degrees at a time. A regular radar would just look in one direction. So there's a variety of different things we could do in the automotive domain. We could reduce the number of elements. So instead of using a large antenna array, we could use only a subset of the elements, but still get the same performance. So I'm going to skip through this. There's a whole bunch of movies that show some of the radar applications, but again, they're all on my webpage, so you could go ahead and take a look. And I will just mention this application. It's radar, but it's radar for clinical. So this is something else that is kind of new work and we're excited about, is that we've been looking at how we could use radar in a clinical setting, for example, to measure vital signs. Okay, so basically the idea is that, you know, the heartbeat will modulate the radar signal, and if now we have new techniques to extract information at very good resolution and very low SNR, then we can now extract these vital signs from the radar signal. So this is something we've been working on kind of recently, and we now have a study in Schneider Hospital in Israel. It's the biggest children's hospital in Israel, where the motivation is clear, right? Like when you have kids, you don't want to strap them to all of these cables to monitor vital signs. So we basically just put a radar on the ceiling, and we can monitor like all the kids in the room and get their vital signs without ever having to connect anything to them. So this is something we're kind of excited about, where it's an example of how we take technology and use it in a clinical setting. So those are the type of things that we like. Let me skip this. This is going back to kind of the cognitive radio, but I'll skip that. One thing before we go into super resolution and AI, so that I end on time. Another nice area where there's nice coupling between physics and algorithms is this domain of metasurface antennas, which is becoming very hot recently. So a lot of people have been looking at how you can use metasurfaces. So basically what metasurfaces are, these are antennas where when you change the current through them, you're basically changing their response. So it's a convenient way of getting kind of large scale, low power antennas. And it's been used a lot recently in communication, mainly as a passive device. So the goal is that, you know, if I have a signal coming from a base station and I have users that are hidden, let's say by this tree, then if I put metasurfaces here, I could, you know, change the current, it will change their reflection, and they'll reflect the signals back to the users. Okay, so a lot of people have been looking at this and using this in a communication context. But what we want to do is, just like all the things we've been doing until now, is not use them as passive devices, but actually use them as active devices and modulate the signals, right? So everything I've been talking about of like, you know, getting all of these aliasing and linear combinations, now I could use a metasurface and, you know, go crazy with the currents, but of course in a controlled fashion. And in that way, modulate all of the signals coming in and coming out in a very active fashion, no longer passive, and totally change the reflections. But in that way, maybe get other advantages than just, you know, going around the tree. So for example, we've been using these, let's say on the receiver side, to say, you know, if a signal comes in, could I take linear combinations in a very efficient way, and in that way reduce the number of antenna elements and reduce the number of bits? So this is one thing that we've been working on. Another thing we've been working on is on the transmit side, is saying, okay, could I now modulate the signals when I transmit them, and maybe in that sense, let's say, focus them in a certain direction very efficiently. So this is actually really cool in 6G networks, because you want to use very high frequency and a large number of antennas in order to convey large data rates. And what we could prove, again, this is kind of going back to the physics, is that when you use large antennas and large frequencies, you're basically operating in what's called the near field. Okay, so signal processing and array processing always consider far field, right? Because there's a linear approximation and everything becomes linear and makes the math much easier. But it makes the math easier, but you lose a lot of the benefit. So what we've been doing is saying, okay, could we actually, again, go back to the physics, go back to these wave equations, right? And focus the waves, now that we have this control on the multiple antennas, in such a way that we could focus not only in a direction. So when you do the linear processing, you could only focus in a certain direction, but I can't focus along the line. But now that we use the spherical wavefront in the near field, I can actually focus to every point in the line, not just on a line. And we could do this, the metasurfaces are almost free, right? They're very cheap. So we could do this practically in a very convenient way. And we could get various different benefits. Like for example, because I could focus on a line, I could separate very close users, okay? So I could get very good interference rejection. We could also transfer energy that way, right? If I want to transfer energy to a specific point, I could just focus to that point. Okay, so this is kind of a cool use of principles of physics to get different signal processing benefits by focusing in a very convenient way. So let me just quickly, I mean, this we already described, so I'll quickly talk about the super resolution and then leave a few minutes for the AI. So we already talked about super resolution and the limits that we have and how we can overcome them with these fluorophores. So just going back to what I said at the beginning, what we do is, again, it's this aliasing concept, okay? So we allow the fluorophores to fluoresce together, but then we kind of project them and use these sparse recovery ideas to recover a high resolution map, even though we take a small number of images. So here, again, it's maybe not so easy to see on the screen, but STORM is the method behind the Nobel Prize. SPARCOM is the work, on this we work together with Professor Moti Segev from the Technion. So this is the method that we've been using, where we're allowing a lot of fluorophores to project, to fluoresce, and then we take these linear combinations and basically recover the map. And this is a learned version I'll talk about shortly. But we can see that we could get very high resolution, even though we're using 2 orders of magnitude less samples. And the nice thing is that because we could do this now quickly, we can now start looking at live cell imaging. So we've been working with Professor Gilad Haran from Weizmann, where he's interested in T cell receptors and basically in their dynamic response. And until now, they haven't been able to see that at high enough resolution, but they have various different hypotheses about what should happen, right? What they think happens in these dynamic processes. And now for the first time, again, getting data from his lab and using our techniques, we were able to actually see these processes at high resolution in both time and space. And this is actually a video. It's a little bit hard to see on the screen, but this is the video that we got from his lab, and this is the super resolved image using our techniques. And of course, by just looking at this, I don't know if it's good or bad, right? I mean, it's higher resolution, but who says it's correct? But lucky for us, and I guess lucky for him, this kind of corresponded to what they anticipated. So, hopefully that means that that the image we got actually makes sense. And we've been looking more generally at how to apply these ideas to biological imaging. We've been working on this also with the Broad Institute, and whoever's interested, we have a recent review where we focus specifically on biological imaging. So this brings us again to the ultrasound example I showed at the beginning, where we inject the contrast agents and then kind of track them. And this is a clinical study we did with Dr. Ahuva Grubstein, who heads the breast unit at Beilinson Hospital. And basically we scanned 20 patients with different types of lesions. And for all of these patients, we had ground truth, right? Because these are patients that we had, MRI, PET-CT, biopsies. So we kind of know, or they know, the doctors, they didn't tell us, but they know, what each patient actually has. And like we said before, just injecting the contrast agents doesn't help. It just makes everything brighter. But here you see, these are 3 images. And you see over here, all of these images look the same, right? If you were just looking at the ultrasound image, you cannot tell, right, what kind of tumor each one of these patients have. And that's why ultrasound is not really used so much, right, for breast screening. It's not a very convenient tool. But if you look over here at the same tumors, at the same lesions after our post-processing, you could see that they're very, very different, right? So here you see that it's very homogeneous, and this is actually a benign tumor. Here you see that there's only fluid inside, and therefore this is indicative of a cyst. And here you can see that it's very non-homogeneous, and this is actually indicative of a malignant tumor. And like I said, these are patients for which we had ground truth, so we know that the results that we got are actually correct.
But here you injected air into.
I inject these microbubbles, yeah. But what's important to note that these are patients that have an infusion anyway. Okay, so they come for like a day. So these are all patients, right? So they come to the hospital for a day of different treatments. And so from their point of view, I'm not doing anything special because they have an infusion anyway. And the doctor is doing the same ultrasound scan they did before. And I'm just injecting, instead of just fluids in the infusion, we're putting in these microbubbles. So from the patient's point of view, there's no difference.
Does that hurt the patient?
No, because they have an infusion anyway. They don't feel the bubbles. No, they don't feel it. It just costs us money, by the way. But there's a cost to it, but a money cost to it, but not from the patient's point of view, it's the same. Otherwise, we wouldn't get
Nerve
volunteers.
injections, they also do ultrasound, and it's terrible.
For what, sorry?
Nerve injection.
Okay.
They do ultrasound.
No. So it's totally macro, right? We don't, like, the patient's connected to an infusion anyway, and we just inject it into the infusion. So they don't feel a difference. Yeah, sure, go ahead.
I have a question. So you knew that the patients, for example, had malignant cancer, but in terms of each of those separate images, then was there a biopsy done to prove that it was a cyst or that it was malignant or?
Yeah. So these patients, that they didn't do for us. These are all patients where they knew this already. They knew what each patient had so specifically these patients were chosen because it's a subset of patients that had MRI, PET-CT, and biopsies. Okay, so there was total ground truth, so to speak, for each one of the patients. But actually, but they didn't tell us that. We didn't know. We just got the ultrasound images. We didn't know what each patient had. So until now, we were talking more about physics and algorithms, and really talking about true physical signals. Okay, which is primarily what we're interested in. But we've also been interested, like everybody else, right? In could we use these ideas to improve AI? So, okay, I don't have to motivate AI to this audience, right? We all know that deep learning has been applied to many, many, many different fields in science and engineering and many more. And of course, there's many things that we could do with AI that we couldn't do before. We get better performance in many different applications. So we could do crazy things, for example, like spawning fake faces. I don't know why you'd want to do that, but there's many people who do. And then, there's things like DALL-E, right? You could say, draw me a picture of a man on, I don't know, an escalator on the moon, and it will do that. So, right, you could do crazy things with AI, which is cool. But in the applications we're looking at, right, we care about different things. So we don't have huge training sets, right? If we think about medical imaging, right, I don't have, hundreds of thousands of images of the same scenario. I'll never get that, right? So we don't have huge training sets. We often cannot do, computationally exhaustive training, especially if we're thinking of, cellular networks when you're doing training on the fly, right? You just can't work with like 100 GPUs, right? I mean, you just don't have the computing resources. Interpretability is key, both in like medical imaging or in, autonomous vehicles, right? Things where there's a price to pay if you make a mistake, right? So if I draw the wrong image in DALL-E, nothing really terrible is going to happen. But if I make a mistake in medical diagnosis, then of course, that has a big price. Robustness and generalization are of course a huge issue that we don't really know how to say, and complexity, right? These networks could be very, very large. So if we go back to model-based signal processing and everything we've been talking about before, right? The nice thing is we have a model. Once we have a model, we could get theorems, we could do optimization, we could prove a whole bunch of nice stuff, and usually we could get inference from very small amounts of data. Moreover, we could say how well we're going to do, right? Like I often know how well I'm going to do even before I do anything. So I know that, worst case scenario, I'm going to get an error of this size. And all of that we, of course, learn when we're doing deep learning. Okay, but so then why do deep learning? Well, of course, there's many reasons, but in particular, for model-based networks, for model-based processing, I have to have a model, and very often we don't have an exact model. The other thing is that maybe I have a model and I can solve it, but it could be very, very slow, right? So clearly there's many advantages of learning, and the question is, could we merge the two? So could we somehow combine model-based algorithms with deep learning? So many, many people, of course, are working on this, and there's many approaches to doing this. Let me skip this. Let me kind of just outline two of the approaches that we've been looking at, and many others. I mean, this is not just our own work. Many people are following kind of this paradigm. So one paradigm is to basically use networks, but make sure that the networks are inspired by an optimization algorithm. And this is what's referred to as unfolding. I'm going to show what I mean by these two things. The other is the other way around, where we use an algorithm. Okay, we're not using networks, we use an algorithm. But any place in the algorithm there's something we don't know, we use a network just to learn that block in the algorithm. Okay, so these are very two simple approaches. And again, we have a recent review with Stephen Boyd where we go into much more detail on these different approaches. So just in a nutshell, the unfolding approach actually goes back to a really beautiful paper from Gregor and LeCun, but only recently has been gaining more traction in the optimization and signal processing community. So the idea is, in model-based algorithms, right, we have some metric function, we have some regularizer, and then you use your favorite optimizer to solve the problem. So typically what it's going to look like is something like this. You have some pre-processing, some post-processing, and then you have iterations of the algorithm. So what you do in unfolding is you write down several iterations, let's say 10 iterations of the algorithm, and I'm specifically saying 10 because we normally don't use more than 10. So you write down 10 iterations of the algorithm. Actually, if you solve this as an algorithm, you'll get a lousy result because after 10 iterations of an iterative algorithm, usually you haven't moved a lot, okay? So you're typically not going to get a good result. But what we do in the last stage is that these iterations in an iterative algorithm, they're just fixed. Now what we do is we free some of the parameters and learn them from data, okay? So basically, our network at the end looks like an optimization solver, but in each layer of the solver, there's parameters that we learn from training data. And the training data very often is just given by simulation, okay? We use the optimization solver to actually generate simulated data. So that's how we could get away with using very small amounts of real data, and most of it is complemented by simulated data. Okay, so this is one approach, and this is a review that we wrote specifically on this approach, so those of you interested could see more details. The other approach is super naive and super simple, but very effective in certain applications, which is we take the algorithm, okay, let's say the Viterbi algorithm, which is a dynamic programming approach to solve symbol detection. So it's an efficient algorithm, right? It's not necessarily a solver of some optimization problem, but it's a good, efficient algorithm. What is the problem? The problem is that it requires channel knowledge. So every time there's something we don't know, like the channel, we just, in that block, we use a shallow network, okay, just for that block. So we leave the algorithm and just supplement it with a block every time there's something we don't know. And what we could show both algorithmically, but we could also prove some of this mathematically, is that both of these techniques, again, depending on the setting, actually allow us to incorporate models and to do it in a very efficient way. So we could prove that we need less training data and we could get better generalization error. So I think I'm running out of time. So let me just, I'll skip this. This is
improper learning.
What?
This is improper learning.
This is, sorry?
Improper learning.
What do you mean by improper learning?
Meaning that you have an underlying simple model determined which you don't know, but you plug in a neural network. The causal functions include the simple model that you don't know, and you run learning on this. This is called improper learning.
So I'm not doing end-to-end learning.
No, I understand.
Yeah.
I understood very well. But basically, you're replacing some unknown model with larger function codes.
So yeah, not really. I'm not replacing them. So let me maybe show an example, and maybe that will be a little bit more clear, okay? And if I don't answer your question, then remind me, okay? So starting with the unfolding, and again, I know I'm running out of time, so I'll just quickly just go through the example. So just as an example, right? We've used this for image deblurring. Basically, we just set up an optimization problem with respect to total variation. Use ADMM. That gives you the structure of the network, and then you learn the parameters from data. So the network that you get doesn't look like any existing network, right? It looks like an ADMM solver. I'm just learning the parameters. So we could use this for various different image deblurring problems where there's heavy noise, where there's just areas that are clipped, very heavy blur. So it's very effective, and it trains on very small amounts of data. And at least from my perspective, the important thing is that it's very principled. I know exactly what I'm doing, right? So I'm setting this up as an optimization solver. This goes back to COVID, what I said before. So we've used this for COVID when we had very small training sets, and we can show that we could get over 90% detection from X-ray, just to show that it's not a trivial problem. So if you look at these images and you had to guess, who has COVID and who doesn't. So this, for example, looks pretty good, right? I would guess that this doesn't have COVID. I mean, I'm not a trained radiologist, but radiologists also would guess that. So this looks, pretty clean. So this looks like it doesn't have COVID, and this actually looks like it does have COVID, but the truth is actually the opposite. So it's not an easy problem, even for radiologists, to detect from X-rays, where there's COVID and where there's not, but the algorithm could actually do it pretty effectively. We could do the same thing from ultrasound. We can use this for more elaborate problems like separating. This is separating blood flow from tissue background. And again, so going back to what you said, like here what we're doing is I'm modeling this as an optimization problem. Like here particularly, I'm modeling this as like low rank plus sparsity. And then I'm using an optimization solver where I'm learning some of the parameters. Maybe I see Shafi's, yeah, we could talk about this more offline. This is the Viterbi net, and maybe this is what you meant by improper function. So I'm still using dynamic programming. I'm doing the same thing as Viterbi, but just the likelihood itself, I'm learning with a network. Okay, so I don't think it's the same thing as improper learning, but we could talk about it maybe after I wrap up. Okay, and this is just some of the theory that we can actually prove that by using these techniques, we get better generalization and we can use less training data. So wrapping up, what hopefully I've got across is that by coupling physics and algorithms, we could do more from less data. And really, like I said, first of all, this leads to new mathematical and physical limits. So that's kind of more of the theoretical side of the story. There's a lot of interesting engineering research actually developing new technology based on these ideas. And at least to me, one of the exciting things where I really hope to collaborate with people who know more about the actual fields is, could we now use this to get different scientific and clinical breakthroughs if we could, track signals faster than we could before and see what we couldn't see before. So at least to me, moving forward, that's kind of more of the exciting part. And I skipped through all of the math. So those of you who are interested, you could find more details, of course, in the papers on our webpage and in our books on the topic. And of course, none of this would have been possible without my amazing group of students and engineers. So all of this, of course, was done together with their amazing, amazing help. And my collaborators that I've had the honor and pleasure to work with and hope to extend to other collaborators as well. And thank you very much for all of your questions and for listening to me for so long.